This video presents the findings of my master's thesis, titled Optimizing Thermal Comfort in Architectural Design, a Climatic Response Study in Dhaka, Bangladesh. We will cover the introduction, problem statement, research objectives, methodology, key findings, and conclusion of this study. Dhaka faces a growing urban heat crisis, largely due to high energy consumption from air conditioning and the urban heat island effect. My goal is to explore sustainable, climate-responsive architectural solutions to improve thermal comfort and reduce energy dependency. The core problem stems from a cycle of increasing heat, excessive cooling demand, and subsequent energy waste. This leads to issues across thermal, energy, visual, ventilation, and economic categories. The main objectives of this research are to identify thermal comfort challenges, evaluate passive design strategies and innovative technologies, and develop climate-responsive design guidelines specific to Dhaka. Climate analysis reveals that Dhaka experiences hot and humid seasons, ranging from 26 degrees Celsius to 32 degrees Celsius, with high humidity. Wind direction changes seasonally, and local residents show a higher tolerance for heat due to cultural adaptation. We reviewed two main thermal comfort models, Fanger's heat balance model and the adaptive comfort model. The adaptive model, considering behavioral, physiological, and psychological adjustments, is highly relevant for buildings in Dhaka relying on natural ventilation. My research employed a mixed method approach, integrating qualitative and quantitative data. The research design was descriptive and analytical, utilizing primary data like field surveys and on-site measurements, and secondary data from the Bangladesh Meteorological Department and existing literature. I used simulation software and comfort indices like PMV and PPD as part of an analytical framework to model design strategies and formulate guidelines. The results were validated through expert consultation and comparison with actual field data. Key findings identified 5 main passive design strategies: optimizing orientation, shading, ventilation, evaporative cooling, and greenery. These methods can reduce indoor temperatures by 2 to 4 degrees Celsius and significantly improve comfort. Optimal orientation minimizes solar heat gain throughout the year. The wind rose diagram shows the best and ideal orientations for maximum natural airflow, considering local wind direction and intensity. Shading involves using architectural elements to block direct sunlight. Recommended window-to-wall ratios, or WWR, for thermal comfort suggest low ratios, ideally below 20%, for a hot and humid climate like Dhaka. Ventilation promotes natural airflow to cool interiors. Effective types includes ingle-side, cross, stack, and hybrid ventilation. The Venturi effect also shows how fluid flow, like air, speeds up through a constricted area, aiding cooling. Evaporative cooling uses water-based methods to lower air temperature. The beehive coolant, inspired by this concept, is an innovative method to reduce heat and cool air naturally as it passes through water-soaked earthen pots. Greenery integrates plants and green spaces for natural insulation and cooling. Vertical gardens, green balconies, and green roofs are demonstrated strategies that facilitate exhaust of hot air and promote natural ventilation. As a case study, Karupanya Rangpur Limited Factory, designed by architect Bayajid Mahbub Kondokar, is a self-sustaining ecosystem. The design prioritizes passive cooling, utilizing evaporative cooling from water bodies and lush greenery to lower the temperature, minimizing the need for air conditioning. To summarize, the study identified the thermal comfort challenges in Dhaka's dense urban buildings. We evaluated various passive design strategies and technologies. These findings ultimately resulted in the development of climate-responsive design guidelines for the region. Thank you for watching this video on optimizing thermal comfort in architectural design.